Have you ever wondered how a company can be so sure a new drug works after testing it on, say, only 25 people? Or how a poll can call an election with just a tiny sample of voters? Well, today we're diving into the powerful statistical tool that makes all of that possible. It's designed specifically for making big, confident decisions with small amounts of data.
Okay, so here's how we're going to break this down. First, we'll set the stage with the main problem, making decisions when you don't have a lot of data. Then we'll introduce the solution, the t-distribution itself. After that, we'll get into the how, the framework of hypothesis testing. We'll look at the different t-tests you can use, and then we'll make it all real with a case study. And finally, we'll talk about why this whole thing should matter to you. All right, first up, let's really frame the challenge that we're trying to solve here.
I mean, think about it. You're launching a new app, but you've only gotten feedback from 20 beta testers. Or you're tweaking a manufacturing process, but you only have a handful of samples to check. How can you possibly be confident that the app is going to be a hit, or that the new process is actually better? This is a huge, high-stakes problem that people face every single day.
Well, the answer isn't to just guess and hope for the best. It's to use a tool that was literally built for this exact situation. It's a method that lets us draw really strong conclusions from small, limited data. And that tool is called the Student's T-distribution.
And that's the perfect segue into our next section. Let's really define what this tool is. Think of it as your compass when you're navigating through the fog of uncertainty. So what is it, really? Simply put, the t-distribution is a type of probability curve that's just perfect for small samples. We're usually talking about fewer than 30 data points. It's built for the real world, because in the real world, you almost never know the true standard deviation of the entire population you're studying. The t-distribution is cool because it lets us use the standard deviation from just our little sample to make a really good estimate about the average of the whole group.
Now, you've probably heard of the normal distribution, right? The classic bell curve, also known as the z-distribution. Well, the z-distribution is great, but it has one major catch. It assumes you already know the standard deviation of the entire population. The t-distribution is way more practical. It works when you don't know that, which, let's be honest, is most of the time. This practicality gives it a slightly different shape. It's a little flatter and wider, with what we call fatter tails. That shape is super important because it's basically building in a buffer for the extra uncertainty that comes from working with a small sample.
And here's where it gets really cool. As you collect more data, as your sample size gets bigger and crosses that threshold of 30, the t-distribution starts to change. It gets taller, it gets narrower, it tightens up, and eventually it basically morphs into the normal z-distribution. Why? Well, it's simple. More data means less uncertainty. The more you know, the more confident you can be.
Okay, so we've got the tool, but how do we actually use it? Well, that brings us to our framework, which is called hypothesis testing. You can think of these as the official rules of the game for making smart, data-driven decisions. You know, at its heart, hypothesis testing is just a structured way of doing what our brains do naturally. You have an idea, a hypothesis, and then you look for evidence to see if that idea holds up. For instance, you might have a hunch that your new ad campaign boosted sales. Hypothesis testing gives you a step-by-step process to use your data to see if you can confidently support that claim, or not.
Every test is basically a showdown between two competing ideas. First, you have the null hypothesis, or H0. This is the default, the status quo. It basically says nothing interesting is happening here, or there's no difference. Then you have the alternative hypothesis, or H1. This is what you're actually trying to prove. It might be that one group's average is simply different from another. That's a two-tailed test. Or you might want to prove that it's specifically less than or greater than something else. That's when you'd use a one-tailed test.
So how do we decide which idea wins? We calculate something called a t-score. A t-score is just a number that tells us how far away our sample's average is from what the null hypothesis predicted. A really big t-score suggests our data is way off from the status quo, which gives us evidence to reject that null hypothesis. It's the key number that helps us make the final call. To actually interpret that t-score, we have to compare it to a critical value from a t-table. Think of this as the line in the sand. If our score crosses that line, we have a significant result. And to find that line, you just need three things: the degrees of freedom, which is just your sample size minus 1, your alpha level, which is your risk tolerance, usually 5%, and finally, whether you're doing a one- or two-tailed test.
All right, now for the really practical part. Let's open up the Consultant's Toolkit. Now that we know the rules of the game, we need to pick the right play.
And choosing the right t-test all comes down to the kind of question you're trying to answer.
In the consulting world, there's a principle called MICE. It stands for mutually exclusive, collectively exhaustive. It's just a fancy way of saying you've organized everything so there are no gaps and no overlaps. You've covered all your bases. And that's a perfect way to think about t-tests. For pretty much any basic problem of comparing averages, there is one specific t-test that is the right tool for the job.
So let's meet the big three. First, you have the one-sample t-test. You use this when you want to compare the average of a single group against some known target. Like, is the average weight of our product actually 16 ounces like it says on the box? Simple. One sample versus one number. Second, the two-sample t-test. This is your go-to for comparing the averages of two totally separate independent groups. The classic example is an A/B test. Did customers who saw the new website design, Group A, spend more money than customers who saw the old design, Group B? This is the workhorse for marketers and product managers everywhere. And finally, we have the paired t-test. This one is perfect for before and after situations. You're testing the same group at two different points in time. For example, you test employee skills, put them through a training program, and then test them again. The paired test tells you if that training made a real difference. It's powerful because each person acts as their own control.
Okay, theory is great, but let's get our hands dirty and make this real. It's time to put all these pieces together and walk through a case study from start to finish.
So, here's our situation. A factory is pumping out tennis balls, and they need to know the true average weight of all their balls. Obviously, they can't weigh every single one, so they grab a small sample of 19 balls. The average weight of that little group is 58.2 grams. The big question is, based on just these 19 balls, what can they say about all the others? And they want to be 95% confident in their final answer.
Don't worry, we're not just going to jump in. We're going to use a clear 5-step process. First, we'll pull out the key numbers from the problem. Second, we'll do a couple of quick calculations for our alpha and degrees of freedom. Third, we'll look up our critical t-score. Fourth, we'll calculate the margin of error. And finally, step 5, we'll build our confidence interval. Let's do it!
Step 1. Identify the inputs. This one's easy. It's right there in the problem. They want a 95% confidence level. This is the bar we've set for how certain we need to be.
The next key number is our sample size, n. In this case, it's 19. Now, what does that number immediately tell you? It's less than 30. Ding, ding, ding. That is our big signal that we absolutely have to use the t-distribution. The z-distribution is not an option here.
Okay, on to step 2. A couple of quick calculations. First, our alpha level. That's just the other side of the coin from confidence. If we're 95% confident, then our alpha, our risk of being wrong, is 5%. Next, our degrees of freedom. That's just our sample size minus 1. So 19 minus 1 gives us 18.
Step 3. Let's find that critical t-score, our line in the sand. We just need to look it up on a t-table using our two numbers, 18 degrees of freedom and a 5% alpha level. And since a confidence interval has both an upper and a lower limit, we're doing a two-tailed test. We look that up and we get our t-score, 2.101.
Now for step 4, calculating the margin of error. This is the plus or minus wiggle room around our sample average. The formula is pretty straightforward. You take your t-score and multiply it by the sample standard deviation divided by the square root of the sample size. So we plug in our numbers, 2.101 times 0.4 divided by the square root of 19. That gives us a margin of error of 0.192 grams.
We're on the home stretch. The final step is to just build the interval. We take our sample mean, 58.2 grams, and we simply add and subtract that margin of error we just calculated.
And boom, there's our answer. We can now state with 95% statistical confidence that the true average weight of all the tennis balls this factory produces is somewhere between 58.008 and 58.392 grams. Think about that. We took a tiny sample of just 19 balls and created a precise, defensible estimate for the entire population. That's pretty powerful stuff.
So let's wrap this all up by answering the most important question. So what? Why should you care about any of this? How does this apply to you?
Look, at the end of the day, this isn't just some abstract formula. It's a practical tool for thinking better. It empowers you to go from a simple gut feeling to a reasoned, defensible judgment, even when you don't have all the facts. It lets you quantify your uncertainty to turn a vague, "I'm not so sure" into a precise, "I'm 95% confident it's in this range." It also gives you the ammunition to intelligently question claims that are based on small studies.
It just makes you a sharper, more critical thinker when it comes to data.
So I'll leave you with this thought. The next time you see a news article or a presentation at work making a huge claim based on a small study, you'll be one of the few people in the room who can ask the right question. You can ask, how can you be so confident with such a small sample? Because now you know exactly what tool they should have used to find that answer. Thanks for watching.